Hey, Ryan, welcome. Would you like to be put in the green room with Pavel and Richard?
No, that's all right for now. I'm
Okay.
actually looking over some homework, to be
No
honest.
worries. I know people use the time before the seminar for a variety of things. So, oh, it looks like Pavel did it.
Yeah, I just got the invitation.
Yeah. Well, you're free not to join. So,
Okay. Um,
All right, welcome back to the main room, everybody. Let's see, Pavel, I'm going to stop sharing. Do you want to go ahead and start sharing your slides and just check your microphone one more time?
Can you hear me now?
Yeah, perfectly.
Okay.
Great,
Good.
thank you. Okay, if you're all set, I think I'll just go ahead and do my little 2-minute spiel at the beginning here and we'll get going. Is that good, Pavel?
Sounds good, Tim.
Okay,
I'm ready.
excellent. All right, well, first of all, welcome back, everybody, to the SMU Physics Department Speaker Series for Spring 2021. And we're beginning today our March series, perfectly on March 1st, and its theme of New Frontiers in Physics. And in a moment, of course, I will introduce today's speaker, Professor Pavel Nadolsky. Now, I want to point out that many of our March talks will showcase research that's ongoing in our own department, and this is absolutely intentional and on purpose. Faculty from a variety of subjects will be presenting their work because the aim here is especially to highlight faculty who've expressed an interest in attracting students to their work, for instance, for the upcoming summer period or beyond. Now, Professor Crystalline Smith kicked this off with the winter colloquium back in December in 2020, which seems like a lifetime ago. And now we have ahead of us almost a whole month of such presentations. And so just so everybody knows, especially to faculty, but also to postdocs, if you want to showcase work that's going on that you're working on in the department, we do actually have an available slot next week on March 8th that we've just not been able to fill with even with external talks. And trust me, we've tried. So if you're interested, let me know. And finally, some of the usual reminders. So to our audience on Zoom, to ask a question, just type the word speak in the chat window to indicate you want to speak, and I'll interrupt the speaker at the next available moment, at the end of a slide, for example, or if it's during the Q&A at the end, we'll just call on you in the order that your comment appears in the chat window. And because we have the mics locked down because we're on a live stream here as well, you'll only be able to speak when called upon by a moderator. And as I've warned you, the event is both being recorded and simultaneously live streamed on YouTube. So hello to our participants on the YouTube stream. Okay, so without further ado, let me introduce today's speaker. So we're very pleased to welcome our own Professor Pavel Nadolsky to speak today. He received his PhD from Michigan State University in 2001, and he conducted postdoctoral work at SMU, Argonne National Laboratory, and Michigan State University before joining the faculty at SMU in 2008. His research concentrates on the theory of elementary particles at hadron colliders, including observations of particles using the Large Hadron Collider. And it combines quantum field theory, computer simulations, and multivariate statistical analysis across a range of experimental data, not just limited to the Large Hadron Collider. He presently serves in at least a couple of leadership positions, including as the co-spokesperson of the Coordinated Theoretical Experimental Project on Quantum Chromodynamics, or CTEQ as it's commonly known. And the goal of that collaboration is to develop widely used parametrizations of Parton distribution functions. In addition, he's also the co-convener of the SNOMAS 2021 Community Planning Meetings Energy Frontier Topical Group 6, which is focused on hadron structure, forward quantum chromodynamics, and hadron spectroscopy. And also, as a fun aside, key equations from his publications have also appeared in the background, like on whiteboards on the set of the sitcom The Big Bang Theory. So now you have to go back and watch all the series that ran from 2007 to 2019 to see if you can spot them. So I'm very pleased to welcome Pavel here today to speak more about his work. So take it away, Pavel.
Thank you very much, Steve. And first, I would like to thank my collaborators, both at SMU and outside of SMU. The results that I will show today are not just my work, but really it's a result. It's an outcome of multi-year effort dedicated to a very broad research program associated with the study of the proton structure. In particular, at SMU, we had a number of students and postdocs who contributed to the results that I will show here. Tim Hobbs, Xiaoshan Jing, Fred Olness, Bo Ting Wan, Bo Weng Wan, as well as the previous postdocs, TJ Ho, Jun Gao, Marco Guzzi, and Keping Sek. This effort is truly a major teamwork. So I would like to give you a review of the status of our field, and it's a major subject. I don't have time to discuss everything in detail, but we'll give you, well, hopefully some feeling about what this area is about. And if you wish to follow up, recently we published two major publication papers. One is about the so-called CTEQ 2018 global analysis of the Parton distribution functions. So this is a paper in Physical Review D that, well, it took us a year to work with the referees to accept it, but finally it was published in PRD as an editor suggestion. And this work shows sort of the main phenomenological results, as well as introduces the parameterizations of the Parton distribution functions that we can use in a variety of collider simulations. And then the second paper is in the Review of Modern Physics. And so this paper focuses more on theoretical and statistical aspects of the analysis of Parton distribution functions. So if you wish to learn how these studies work and what goes into essentially what happens under the hood of these studies, so this is a review that I encourage you to read. So let me start with this beautiful picture which shows the main protagonist in this talk. This is actually not the real picture, but the visualization of a proton that I will discuss today by an artist who is stationed at CERN. Now, this is a beautiful picture. It looks like some Christmas decoration. Now, of course, the proton does not consist of balls and confetti, but it is a far more complex quantum objects. But nonetheless, this picture reflects the whole complexity of the internal structure of the proton. Now, the proton consists of more primordial objects called quarks, antiquarks, and gluons. And quarks come in several flavors. So there are 5 dynamic flavors inside the proton. So up, down, strange, charm, and bottom. And the gluons carry the fundamental force that binds these quarks and antiquarks together to form a bound particle called a hadron. So the force associated with the gluon is called the strong or nuclear force. And this is the only fundamental force that exists both in perturbative and non-perturbative regimes. So I will explain in a minute what this means, but essentially there is a fundamental theory called quantum chromodynamics, which tells you that this binding force carried by the gluons is very weak. It's kind of like an electromagnetic force when the quarks are packed very closely together. But when we pull the quarks apart, this strong force really becomes strong. And so there is basically a string-like excitation field existing between the quarks and antiquarks that prevents them from going away. So that this force really behaves like some sort of elastic glue that keeps the quarks and the antiquarks together inside the protons. And so then the protons are used in many experiments, in particular at the major physics facility called the Large Hadron Collider at CERN in Geneva. So then to make predictions for the Large Hadron Collider, we need to know probabilities for knocking out particular types of quarks, antiquarks, or gluons from the proton. So this probability are described by Parton distribution functions, so or PDFs for short. So this is well, actually, the other meaning of the PDF is the probability density function. Well, Parton distribution functions, they are in fact particular kinds of probability density function, and I will show what kinematic variables go that determine this probability for finding quarks and gluons inside the hadron. So now the study of Parton distribution functions is a major part of QCD, and it's also a very interesting subject. Now, it's also a fascinating subject from the physics viewpoint. I will try to emphasize a number of times why, but let me give you one quick illustration. Well, here is the picture of our universe on a logarithmic scale, showing essentially all typical structures inside the universe on the scale in meters that is shown on this ruler. And so the partons that are little objects inside the proton. So the typical size of the object that I will discuss is something like 5 times 10 to the negative 20 meters or less. So these are the objects that we are able to see inside the proton when we collide them inside the LHC. Now, the LHC itself, as you may know, it's probably one of the largest structures that was ever built by humans. Its radius is about 10 kilometers. And so that, therefore, okay, so you see that basically LHC falls on a very different part of the scale. So it's essentially one of the major facilities that was ever built by the humanity. Now, so then we have this very large difference of scales between the scale of the objects that we study and the size of the LHC. And so again, to give you some intuitive perspective how large this difference is, suppose we take the Parton and we increase our scale so that the Parton becomes about the size of the human. So let's say the Parton becomes of the size of about 1 meter. So then if we proportionally scale the size of the LHC, so the LHC will become the size of the Milky Way. So essentially this experiment is quite fascinating because we use, well, a facility that needs to apply a huge zoom factor to see the tiny objects inside the proton. And furthermore, we can learn a lot about these objects and we can predict very precisely how these objects behave. Okay, so then let's talk a little bit about the physics of these studies. Well, the Large Hadron Collider really works like a major microscope. So what it does, it shoots the objects of a particular energy associated with the specific resolution scale or the specific resolution wavelengths. And by increasing energy, we can see smaller and smaller objects in the collision of the particles. So for example, if we take the particle experiments at the beginning of the previous century, so the energy was only high enough to resolve atom and the nucleus surrounded by the electrons. But as we increase the energy, we are able to zoom in on smaller and smaller areas inside the particles. And so this is indicated by the red rectangle in this diagram. So by increasing the energy, we zoom in inside the red rectangle, and then inside the nucleus, we see the components called the nucleons, or the proton and the neutron. And gradually, we start seeing what I call the valence quark colored areas inside the nucleons themselves. And so these valence quarks, well, they are pretty sizable objects that carry a new type of fundamental charge called the color. But then as we keep zooming in on the valence quarks, we start resolving additional structures inside the valence quarks. And so then eventually at the LHC, we find that the valence quarks themselves are composed of these relatively weakly bound quarks and gluons. So then, therefore, the short distance probe, like a virtual photon heavy boson or gluon, resolves increasingly small structures inside the nucleon. And then, therefore, we need a particular kind of function to describe the probabilities for finding these components of the nucleons called partons. And so the structure, the functions that I will work with today are called unpolarized collinear Parton distributions. So they're given for each type of the Parton flavor A. And so then the Parton distribution function that I will show depends on two major or very important variables. One is the momentum fraction x carried by the Parton A inside hadron H. And the second important variable is called the resolution scale. So depending on the slide, it will be denoted as either Q or mu. So then the contents of the proton in terms of the Parton constituents varies with the resolution scale. So for example, as you saw on the previous slide, if we increase the resolution scale, we are able to resolve what are called C quarks and anti-quarks inside these big blobs associated with the low energy valence quarks. So then the parametrizations for these Parton distributions are very important for a variety of predictions. And so here I show the parameterization that we published last year called CTEQ-TEA parameterization of Parton distribution functions. So these Parton distributions cannot be computed from the first principles. So this glue-like interaction between the quarks that I described is very complex, and so we cannot predict it starting, let's say, from the fundamental QCD Lagrangian. However, we can determine parameterizations for these Parton distributions from a number of precise experimental data sets. For example, from EP Collider, HERA, LHC, Tevatron, fixed target experiments. So we can calculate the parts of the theory cross-section that are needed to make predictions for these experiments to a very high accuracy. And so the current accuracy for these calculations is so-called next to leading order, or NNLO accuracy in QCD coupling alpha S. So then we actually don't know much about this parameterization, Parton distribution functions, and we don't even know what the parametric forms we should use. So therefore, when we determine the PDFs, we provide not just one central prediction, but we provide an uncertainty band that you see in this picture that is associated both with the experimental uncertainties, but also with the parameterization uncertainty and other uncertainties. And so I will discuss a little bit how these uncertainties are estimated. We provide these pattern distributions in a form that is very convenient to use in a variety of experimental simulations. So by now, the LHC collaborations, both Atlas and CMS, but also LHCb and ALICE, did multiple measurements in many orders of magnitude, and the majority of these experiments need accurate proton PDFs. So the estimate of the uncertainty on the PDFs is highly important phenomenologically. So essentially, it will, for example, will allow us to impose systematic constraints on new physics searches by knowing how well PDFs are constrained. Not only that, so as we move towards let's say the next decade of the operation of the Large Hadron Collider, we need to know Parton distributions very precisely for many applications. For example, a very important task is to predict precisely the cross sections for so-called electroweak precision measurements. So this is for Higgs boson production, but also for WZ production, as well as for the processes where we produce several heavy vectors or electroweak bosons together. So then it turns out that in many of these electroweak precision measurements, the uncertainty due to the PDFs plays a very important role. And what you see in the right-hand side figure, well, these are the projections for the accuracy of the measurement on various electroweak couplings. You see two kinds of bars in this figure. So the green bar corresponds to the most optimal measurement where we were able to reduce the PDF uncertainty. The dashed bars correspond to the case when we could not reduce the PDF uncertainty to the optimal level. And as you see, for quite a few measurements, there is a substantial effect of the PDF uncertainty on the projected sensitivity of the high-luminosity LHC to a variety of couplings. Then let's talk a little bit about the calculations for these predictions. So we rely on a major principle in quantum chromodynamics called factorization. And what this means, first of all, is that when we factorize the prediction for the hadronic cross-section, we rely on this property of the perturbative nature of strong interactions that I already mentioned. So namely, each strongly interacting particle will carry a charge called alpha S. And so the charge depends on the resolution scale or the Q. So the larger the resolution scale or the shorter the wavelength is, the weaker the charge is, as is shown in the figure on the left. Now, on the other hand, if the resolution scale is quite low, the coupling charge becomes very large. And so therefore, the perturbative QCD interaction that, for example, is associated with the production of the Higgs boson is now replaced by some very complex non-perturbative interaction that involves multiple quasi-perturbative or fully non-perturbative particles. So the long story short, the hadronic interaction exists in two regimes. So one is in the regime of the so-called asymptotic freedom, which corresponds to this large scattering scales and or small charges, and the other regime corresponding to the confinement. So then to predict our hadronic cross sections, we need to properly estimate both parts associated with the small and large distance contributions. So, for example, one of the major contributions of our group to the LHC physics was the discovery of the Higgs boson in so-called diphoton production mode. And so you see a typical event for photon pair production. Well, unfortunately, sorry, I should have updated it. It is from our competitive collaboration, CMS. but Atlas has similarly impressive figures showing how the Higgs boson is produced and decayed into a pair of photons. So a large part of the uncertainty on the cross sections for the Higgs boson production is due to the knowledge of the strong coupling alpha S, but also due to the uncertainty on the PDFs. So suppose we wish to calculate the cross section for this process. We apply the factorization formalism sort of in the form that I described to you. So, here is a diagram that corresponds to the Higgs production and decay into a photon pair. If we want to calculate the probability of cross section for this process, we evaluate the complicated expression on the right, which consists of the integrals of the so-called hard or short distance cross section that can be computed perturbatively with Parton distribution functions, FA, which these are essentially the Parton distributions that I showed you on the previous slide. And so these Parton distribution functions are non-perturbative. So then we basically, what you see in this case, we need to compute this expression for all possible flavors A and B that can contribute to this process. So therefore, we to make a precise prediction, we really need to know the Parton distribution functions for a variety of flavors in this case. Even though, of course, this process is mostly dominated by the gluon PDF. So now this is a typical example of the calculation that you will use. For any process at the LHC, you will write the hadronic cross section as a convolution integral of the hard cross section with the PDFs. So then something very interesting has been happening in the last, let's say, 15 years. So the quality of our predictions for the perturbative short distance cross sections greatly improved because of a variety of new theoretical techniques that were introduced and automated calculation of these quasi-freak interactions of patterns very effectively. So then, when predicting the cross sections, we know the perturbative short distance cross sections quite well. But then to really get take advantage of this plethora of new calculations, we also need to know the PDFs to comparable accuracy. So the PDFs, on the other hand, cannot be calculated using a clever algorithm, but we need to come up with a systematic and a very, let's say, very careful way for extracting the PDFs from the data. So essentially what we need to do, and this is a typical approach called the global QCD analysis, we take a relatively small number of experiments which are sensitive PDFs and which are relatively clean. So their radiative corrections are not very complex. And then we perform a global fit of these experiments using flexible parameterizations of PDFs. We extract both the central PDF parameterization corresponding to the maximum of the log likelihood when describing this data, but also we extract the uncertainty on the Parton distribution functions. And the uncertainty, as I mentioned, is important for a variety of applications. And so then using these PDFs, we can make predictions for new processes, like, for example, for Higgs production or associated W Higgs production here. And then as we accumulate more data, we can start using more experimental measurements to constrain the PDF. So basically, we close this loop and we introduce more and more experimental measurements to obtain more and more precise Parton distribution functions. So that's kind of the gist of the approach that we use to find the PDFs. Now, of course, the full details of this analysis are very expansive. And so if you really wish to find the very precise modern PDFs, you have to think about three major topics. You have to have very precise and understood experimental measurements. You have to have precise theoretical predictions. But then the analysis that we perform is a large-scale statistical analysis. And so you also have to come up with a variety of clever ideas to extract this uncertainty and basically convince first of all yourself, but then everyone, so that your estimate of the uncertainty is reasonable. Now, this is totally not trivial because the Parton distribution functions depend on many parameters, and I will show you what some of the issues are. In fact, just to make it a little bit closer to what you might be interested, I posted a mystery graph on the Zoom chat, and I invite the speakers to think what is shown on this chart and to label the axis. And then when in a few minutes I get to this graph. But this graph, it turns out, well, everyone probably knows what it is, and I hope, well, especially the graduate students should try to answer in the chat what this graph is showing. So please type your answers or suggestions for the labels, right? But the shape is actually very important for what I will be discussing in a minute. Okay, so I will go to the next slide, but I uploaded the copy of this chart in Zoom. So let's see if how many suggestions we will get as I continue discussing this subject. Okay, but now let me talk a little bit why this statistical analysis of PDFs is it's kind of a deep statistical problem. So the main difference is that let's say between the so-called electroweak precision fits of the standard model parameters and the PDF fits is that in the case of the PDF fit, the theoretical model, which is given by the PDF parameterization, is not uniquely fixed. So what this means, therefore, let's say when we test parameters of the standard model using an electroweak fit like Z-fitter, so our model is fixed. So therefore, the only uncertainties that come out from this fit are due to the uncertainties from the data and maybe theory. But in the PDF fit, the theoretical model itself can evolve to avoid, let's say, experimental constraints. And therefore, there is an additional important class of uncertainty that arises in this PDF fits that is associated with the choice of the functional form. So the functional form can change within some limits. In fact, this uncertainty is quite important, and it's also very difficult to estimate. So the uncertainty due to the PDF functional form contributes as much as about 50% of the total PDF uncertainty in modern fits. Well, that's one aspect. So basically, our PDF analysis has this very interesting property, but also if we go to the next to leading order accuracy, there are a variety of effects that can contribute to the total uncertainty. And again, I show this slide here to show this kind of interconnected map of various issues that we need to consider. Well, these issues, clearly they require very careful analysis. And in the end, we need to somehow include their effect on the PDF uncertainty. So therefore, if I were to classify what kinds of PDF uncertainties arise, we can generally categorize the uncertainties in 4 different classes. First of all, there is an experimental uncertainty. So it's the same uncertainty that would, for example, arise in the electroweak precision fit. And in fact, the experimental uncertainty is the easiest to understand. So for example, if we wish to understand to find one standard deviation on the PDF, assuming all the rest of the parameters fixed, we can apply the so-called delta chi-square equal 1 criterion, meaning that the increase of any PDF parameter by 1 standard deviation should correspond to the increase in the total chi-squared by 1 unit. So this is the criterion that I will discuss in a minute. But then there are other equally important uncertainties. In fact, they are more important in many cases than this experimental uncertainty. So there are the theoretical uncertainties, parameterization uncertainties, such as the ones associated with the functional form, as well as a variety of methodological uncertainties. So like, for example, we could we can vary the selection of experimental data sets, or we can vary the fitting procedures. We can vary our definition of the goodness of fit. So what constitutes a good fit in this case? And all these variations will result in some variation of the final PDF parameterization form. So then, in fact, when we publish the CTEQ-TEA PDF, we do include an estimation of all 4 kinds of contributions. And so the final uncertainty on the CTEQ-TEA PDFs includes the contributions from all 4 sources. I don't have to discuss in detail how we do that, but you have to remember that there are these 4 major classes, and the final uncertainty, well, at least in the case of our CTEQ-TEA Parton distribution functions, is the sum of these 4 contributions, right? So, given that this is a colloquium, I will very briefly show some technical slides that may be interested to, especially to the users of our PDFs. When we publish our CT18 PDFs, we realize that even with our systematic approach, it is very difficult to construct the full uncertainty, let's say, that includes, for example, the theoretical variations or the variations due to the choice of the experiments in one parameterization forms. So therefore, in the CT18 paper, we published the default CT18 set. That now this set is very good. You can use it in most cases when you don't particularly care about the details of the PDF dependence. But then we also found it important to include 3 additional sets called, now the most extreme set is called Z, but there are 2 intermediate sets called A and X. And so the difference between these sets A and X and Z is first related to the inclusion of the very precise measurement from Atlas called the 7 W and Z production data. That unfortunately, it is a very precise measurement, but unfortunately, it shows some tension with the other experiments that are that are included in the CT18 analysis. And then another choice that we make is to approximate the effect of small x saturation effects. In the CT18X and Z fits, we introduce a special factorization scale that to a very good effect mimics the effects of the small x or BF Keller summation. And so it turns out, because of the interconnected nature of the global fits, the changes that we make in the small x region in fact propagate into the uncertainty on the PDFs in the large X region. So therefore, it is not possible just to isolate the small X resummation effect, but for example, through the sum rules, they will also affect the behavior of the PDFs at much larger X than as compared to where the small X resummation are important. So now, very briefly, I will show you how this new CT18 and CT18Z PDFs differ from the previous set of PDFs that we published called CT14. So in fact, the differences are not that large. So the differences are not that large. Well, the CT18 is very consistent with CT14. Now, CT18Z has a somewhat different shape, especially at low invariant masses, like about 10 or maybe 20, 30 GeV. And that's the effect of including the approximation to the small X resummation in the CT18Z. Now, here I show similar figures, but now they show the normalized uncertainties on Parton luminosities, the QQ and GLU luminosity. Well, in this new fit, we include a lot of new data from the LHC, but unfortunately, for the reasons that I will explain in a minute, the uncertainty does not go down much, even though we include additional measurements from the LHC. Now, for example, you can see that the error bands on the left-hand side shrunk a little bit after including this new LHC data, but the uncertainty, let's say, on the Higgs boson production cross-section or TT bar production cross-section, well, they change, but not by a lot. So basically, it seems that the LHC data that we include still cannot compete against the other data from, let's say, from deep inelastic scattering or from the Tevatron and Drell-Yan experiments. One of the tasks for us is to understand why this happens.
Sorry, let me interrupt for a second. We had a question from Bob. Let me get him unmuted here.
Yeah.
No, that's okay. That was 3 or 4 slides ago. We'll just go ahead.
Okay.
Okay. Well, now the other interesting question is, well, you can perform this analysis in a number of ways. And there are 2 other groups that perform a similar analysis and include the similar data. So the differences between, let's say, CT18 analysis and the contemporary MSHT and NNPDF 3.1 analysis are reflected in these plots of the Parton luminosities that you see on the top. In fact, some of these differences fall outside of the nominal bands that are provided by the groups that published these PDFs. And one interesting question is why it is. So why is it so? So even though I mentioned that we put a lot of effort in understanding a variety of uncertainties, but still there are cases like, for example, for the GLU quark luminosity in the second sub-figure in the upper row, where the NNPDF prediction is quite different from the CT and the MMHT prediction. So these differences, well, are hard to understand. In fact, they require so-called benchmarking comparisons between the fitting frameworks of different groups. And one of the efforts that is going on right now is to perform these benchmark comparisons and come up with the so-called combined PDF for LHC Parton distribution functions, which will be published probably sometime next year, which will combine the uncertainty bands from these three groups, but also will hopefully reconcile and maybe eliminate some of the differences that you see in these figures. Okay, so here is a quick summary of how the CTEQ-TEA analysis was performed. Again, I can come back to it, but I don't have much time to discuss it in detail. Well, now essentially, first of all, we need to select LHC data sets that may have high sensitivity to PDFs. And we use two new approaches based on so-called fast Hessian techniques that are, well, one of them was developed at SMU. And I will explain why these techniques are useful. Then we need to provide theoretical predictions for these new LHC data sets and provide them in the form that will be convenient for the global analysis of Parton distributions. We need to properly understand uncertainty in the resulting PDFs, and a lot of effort went into it. So in particular, to understand the uncertainty on PDFs due to the choice of parameterization form, as well as due to the QCD scale dependence. You can read about it in our paper. But finally, well, there is also a major issue of complexity in these fits, and in particular, this because of including the new data sets and high precision, these calculations become very CPU intensive. So in the case of the CTEQ-TEA studies, the availability of the high performance cluster at SMU mainframe, which we used to do the parallelized calculation, made a major difference. So we were able to publish our results before the competing group. And so a large part of it is due to the fact that we had the mainframe available. So mainframe is clearly playing an important role for our studies of PDFs. Now, here are the data that are included in the CTEQ-TEA analysis. I just briefly mentioned the classes. So the fixed target DAS and the deep DAS or deep inelastic scatter data play a very important role in constraining Parton distributions at relatively small values of the factorization scale mu over a very large range of momentum fraction x. Then inclusive jets, both at the LHC but also at the Tevatron, play a major role in constraining the PDFs. In fact, the CMS is 7 and 8 TV data sets provide probably the most important constraints on the CT PDFs, and somehow they are even more accurate than the Atlas measurements. The W and Z production at the LHC plays an important role, as well as the new measurements like TT bar production or ZPT start placing some constraints, but unfortunately, these data are not sensitive enough yet to constrain the PDFs. Well, here are the data sets that we include in our analysis, and listing only the new LHC experiments. As you see in the CTEQ-TEA analysis, we include a number of measurements on W and Z production. And for example, the lepton charge symmetry measurements are very useful for constraining the separation of flavors between the Parton distribution functions. We also include inclusive jet production both from CMS and Atlas. And then we also include a few new measurements such as high PTZ production or TT bar differential distributions. And those are not very, as I mentioned, they do not make much difference yet. But these distributions are very interesting in the following sense. So we can estimate what is called the so-called sensitivity of the various experiments to various combinations of Parton distributions, or let's say to the average, to the gluon or U quark or U bar on average. And this is shown in this. The sensitivities are shown in this colorful diagram that was developed at SMU. Now, probably, okay, so if I have time, I will explain how the sensitivity works. Essentially, it is a quick way to estimate the magnitude of the pulls on the chi-squared from various classes of experiments. So you see here in this case, the experiments and their classes are shown on the vertical axis, and the PDF flavors to which these experiments may be sensitive are shown on the horizontal axis. And then the closer the color is to the dark red, the more sensitive these experiments are to the specific Parton flavor. Then the experiments come with a different number of points. And so, for example, you could have an experiment that has very precise individual points, but because it has a relatively small number of data points, let's say only 7 or 8, in the full fit that includes about 4,000 of data points, these experiments may be lost. It may not produce a full effect. And so this is precisely what happens with the ZPT and TT bar production experiments, because the TT bar production, in fact, has a very high sensitivity to a variety of flavors per data point. And so therefore, if we had, let's say, 1,000 TT bar data points, we would get, with very precise data points, we will have a very high sensitivity to a variety of measurements. But unfortunately, they only have just a few points per experiment. And what this means, therefore, is that even though these new experiments are included, they still cannot make a significant impact on the PDF fit. Now, furthermore, not only that, but it turns out that several LHC experiments do not agree with one another. So therefore, if you take the new LHC experiments in totality, these LHC experiments are shown by the red stars on the right-hand side. So if they were to provide a consistent message, so these experiments will start to be competitive with the deep inelastic scattering experiments. So unfortunately, there are some tensions between the LHC data. And because of these tensions, we are not able yet to obtain a significant constraints from the LHC on the Parton distribution functions. In fact, if we look at the total sensitivity, what happens is that the Hera deep inelastic scattering still plays the major role, as well as the fixed target deep inelastic scattering experiments such as BCDMS and NMC, but also the mid-size Drell-Yan experiments such as, in particular E605, E866, provide very competitive constraints that are not beaten yet by the LHC data. Now, that said, of course, what I mentioned to you is that if you look, for example, at the CMS7 and ATV jet production, so these measurements are relatively precise, and they have a relatively large number of data points. So therefore, they start providing important constraints on the Parton distribution functions. On the other hand, the experiments like TT bar or WO symmetry or high PTZ production have a quite a high sensitivity per data point, but because they only have about 10 or 20 data points, they have the relatively low overall sensitivity. Okay, so then the message from this is that the LHC is still has to compete against the other experiments, and really to let's say to get ahead of the deep inelastic scattering, we need to make the LHC measurements of sensitive to PDFs compatible with one another. All right, so then let me talk a little bit about methodology, and okay, so to talk a little bit about two different kinds of PDFs. So one question that we constantly get is that people ask what kind of PDF set I should use in my specific my specific analysis of experimental data. Well, the answer is quite involved, and I will not be able to answer it right now. I will refer you to the other publications that discuss this question in a great detail. But for example, I would like to talk about two differences in approaches for estimating the PDF uncertainty. Both approaches are valid. So one is based on so-called Hessian PDF eigenvector sets, and so most of the groups use this approach. And for example, the CTEQ, MMHT, ABM, Hera groups, they provide the so-called Hessian Parton distribution functions. Now, there is another approach that became very popular in the last few years, and it is based on so-called a neural network parametrization approach. So basically, in this case, the PDF parameterization forms are given by very flexible functions, given the parameterized by the neural networks. And then you can sample a variety of parameterization forms using Monte Carlo sampling. And so then the NNPDF approach gives you not just, let's say, about 50 sets, like in the case of CTEQ, but it can give you 100 to 1,000 Monte Carlo PDF replicas that try a variety of parameterization forms. Now, both of these approaches can be used to predict the uncertainty on the PDF sensitive variables. So the question that people ask is one approach better than the other? Well, so in fact, what you learn by working with these techniques is that we cannot say that, let's say, NNPDF that is better than the Hessian approach or the other way around, because they have complementary strengths and weaknesses. And let me just illustrate it by talking about geometry of these multivariate probability distributions and the curse that affects us all, which is called the curse of dimensionality. Now, did anyone figure out what the figure was about?
Nobody put anything in the chat window.
Okay. Okay. So, but this
and
is.
I'll have to admit, I've been staring at it and sitting here crippled with self-doubt, Pavel. So I'm actually not sure. Yeah.
All right. So basically, it is related to this curse of dimensionality. Okay. So let's talk a little bit and where this curse comes from. So now, okay. So in the case of PDFs, this curse is related to the fact that PDFs depend on multiple parameters, right? So for example, if you take a typical PDF set, it may depend on somewhere from several tens to several hundreds of free parameters that describe the parameterization form. So then one big challenge for the PDF analysis is to come up with the parameterization form that is informative enough, inflexible enough, but on the other hand, it does not fit the noise. So then it's a big challenge to understand how to choose this parametric form. Well, now in the CTEQ case, we use an approach based on the so-called Bézier curves. And so the Bézier curve is something that you probably encountered in vector graphics programs like a PowerPoint. So if you draw a freestyle curve, so you can control its shape using the handles like in this animation on the right. And if you see such a parameterization, so basically this curve is given by the Bézier curve. So it can approximate a variety of functional forms, and furthermore, it's relatively simple in implementation. So in fact, what we find in our recent work, if we look at the PDF fits, so this Bézier curve are as good as parameterizing the PDFs by much more complicated neural networks. But even in this case, these Bézier curves will depend on something like about 28 parameters. Now let's think about the probability in this 28-dimensional parameter space. So for example, when we feed the CT-PDFs, we must try these various parametric forms. And so here is a figure showing how our predictions for CT18 PDFs vary when we vary the parametric form and nothing else using the same setup. And as you see, you can get a very large spread of predictions, especially at small x and large x, depending on the choice of the parameterization form. But then we need to provide an uncertainty estimate that includes the effect of this parameterization dependence. And so here we run in trouble associated with the geometry. So the figure that you saw, it's nothing but the volume of a unit ball in n dimensions. So then the number of parameters n is shown on the horizontal axis, and the volume of the ball is shown on the vertical axis. And so then now, obviously, you expect the volume of the ball to grow as you increase the number of dimensions. But in fact, it only happens up to a certain point. And after about in n equals 6, the volume of the ball starts going down. So for example, if we take 28 parameters, the volume of this ball will be something like 10 to the negative 4. Now, so what does it mean? So remember, I told you that the experimental uncertainty typically is associated with the delta chi-squared equal 1 criterion. So therefore, if we assume that we have a fixed parametric model, so then the only allowed PDFs lie inside the unit ball in n dimensions that has the unit radius. So basically, it has the unit radius. But if we work with the 28 dimensions, the volume of this ball is 0. So therefore, if we try to assemble the PDFs around this n-dimensional ball, in fact, most of the time we'll miss it. So well, here's another way you can see it. If you take a one-dimensional Gaussian distribution, then with the unit widths, then 68% of the replicas sampled from this distribution will be lying in the interval between -1 and 1, right? So this is familiar. Suppose now we take a 28-dimensional or 25-dimensional distribution in this case, right? So then you can very easily show that, because of the large number of dimensions, any replica will have a high chance to be several sigma away from the central fit. And so in fact, the average distance of a replica from the central fit will be about 5. So it's about 5 times more than the radius of the unit ball. And so what this means, therefore, is that a typical replica sampled from an n-dimensional distribution will be abnormal in some way. It will be normal in many ways, but it will be abnormal in a relatively large number, or let's say a large number of directions. And therefore, if you take, let's say, Monte Carlo replicas for either from NNPDF or from CTEA, so those replicas, those green lines that you saw, they are actually quite bad fits. So each of these bad fits will be each of the replicas from from NNPDF is a bad fit, and it is many sigma away from what would be accepted as the best solution. So therefore, the Monte Carlo NPDF replicas really do not probe the close vicinity of the best fit. So they are simply not designed to probe it properly. So the method is not efficient for doing that. It is efficient for other things, but not for probing the close vicinity of the best fit. Then the Hessian PDFs, on the other hand, well, they are very powerful for getting very close to the best fit. And so, for example, you can use a so-called Lagrange multiplier scan, where you can explore the profile of the chi-squared for the whole global set of data, but also for individual experiments quite closely, and you can get to the global fit, let's say, within the few units of delta chi-squared as closely as possible. And so then in the CTEQ-TEA analysis, we actually perform these very unique studies where we study how the the global profile of the chi-squared emerges from the constraints from individual experiments. And so we could plot these profiles either as a function of any parameter, either the alpha s, and from this we can obtain the quite precise determination of the alpha s value at the scale of the Z boson mass. Or we can take, for example, a value of the PDF at a particular x and mu value, and we can do this profiling of the Lagrange multiplier scan on for any PDF, like for example for the gluon at x equal 0.01. Now, so now the only thing with these fits is that they are very slow. And for example, each of the figure that you see here takes about 6,500 core hours on mainframe to produce. And so again, the availability of mainframe was essential for understanding the origin of the constraints from experiments on a variety of functional forms. Well, we have another tool in our box, and I will very briefly tell you about it, which are called so-called fast approximation to global PDF fits. And so there are two techniques called PDF reweighting and PDF profiling that are widely used. Now, unfortunately, these techniques are also misused very often, and so there are very subtleties that are not accounted for when people use this reweighting technique. So if you are interested in detail what happens, please read the Appendix F in the CTEQ-TEA paper. Now at SMU, we developed a new technique, which is essentially it's a fast approximation to this Lagrange multiplier scan that you just saw, and it is called the L2 sensitivity method. So essentially, the L2 sensitivity method allows us to understand the pulls on the chi-squared from the Lagrange multiplier scan, but using the approximate prediction, which is very fast. It is based on the existing PDFs, and we can get much of the same information that we get with very precise, slow Lagrange multiplier scan, with some moderate loss of accuracy, but very fast. And so we use the so-called L2 sensitivity technique to obtain the estimates of the chi-squared pulls, but now over a large range of x and mu. And so just very quickly to show how this works. Well, so very briefly here. Well, I can get back to it, but you saw the plot for showing the Lagrange multiplier scan for the gluon at a particular value of x, which is equal to 10 to -2 in this case. We can obtain very much the same information from the L2 sensitivity study, and it takes about 15 core minutes to produce the figure like this. And now you see you can cover the whole range of x, and you can see the positive or negative value of each curve corresponds to the positive or negative pull on chi-squared from a given experiment shown in the legend when we increase the gluon by 1 standard deviation at the x value shown on the horizontal axis. And so what therefore means is that we can actually study opposite pulls or tensions that arise between the experiments that constrain the gluon, let's say, in the region of X that is relevant for Higgs production. Now, just to talk about something that was very recent. Well, last week there was an article in Nature that published the results of the new experiment called CTEQ-TEA at Fermilab that measured the so-called d bar over u bar asymmetry as a function of the momentum fraction x. And what they found is that the previous result from the E866 experiment that suggested a suppressed d over bar ratio at x above 0.3 is no longer supported by this new measurement from CTEQ-TEA, which, well, now the main difference from E866 is that this new measurement from CTEQ-TEA has a more careful estimate of the systematic uncertainty. So the theoretical models did not like this turn down of the d bar over u bar, which was preferred by NuC. And this new CTEQ-TEA measurements actually prefer a kind of a flatter dependence, but they also prefer the d bar over u bar ratio above 1 everywhere. That is more consistent with the various theoretical models of proton structure. So then one question that we may ask, well, here you see the prediction from CT18, right? So then you can ask, well, what happens with the other experiments? What kind of d bar over u bar ratio they prefer? Now, is there something peculiar about this E866 experiment or other experiments that will also prefer this dependence? And so lo and behold, it turns out that the sensitivity method is very powerful for checking that, because, well, here you see the L2 sensitivity for d bar over u bar ratio. And now you see classes of experiments that provide the strongest pull, chi-squared pulls associated with d bar over u bar. And so then you see, well, one feature that you see in the previous figure, that the E866 experiment, which is 203 here, E866 ratio, it does prefer somewhat lower d bar over u bar ratio as compared to other experiments like NMC line 104 or HERA 160. But also what's very interesting, in fact, the major difference between the E866 and HERA happens at a somewhat lower x values. It's at about 0.1. So well, in this region, well, clearly the E866 experiment prefers something very different from HERA and the NMC. So therefore, clearly, well, there is something peculiar happening. And so the sensitivity method tells us, well, that this E866 experiment, well, need to be further scrutiny. And so one interesting question is whether this new measurements from CTEQ-TEA that do not like this particular behavior d bar over u bar will be supported by other measurements. Okay, so I'm almost out of time, and so maybe if I have 5 minutes, I would like to just conclude by 3 minutes. I'll talk a little bit about what happens with the PDF analysis in the future. Now, first thing that I would like to say is that, well, I very briefly gave you some examples of what we have been doing recently, but clearly there are a large number of topics that are associated with the determination of PDFs, and I listed some of them on this little diagrams here. So SMU actually contributes to many areas in the studies of PDFs, and just like one example, this year or last year, the SMU group with Fred Olness, Steve Sikula, Tim Hobbs published a very interesting study of the new measurement of charm PDFs in deep inelastic scattering. But there are also other contributions from our groups, like, for example, the XFeater program, which is a very powerful tool that is necessary for studying the PDFs. So where are the PDFs going nowadays? Well, there are new tasks emerging for the PDF analysis in the LHC era, and so I'll quickly flash you the slide, what we need to do to, let's say, bring up the PDFs to the accuracy needed for the high luminosity LHC measurement, and I can come back to it. So then there is a new major new facility envisioned for studying the PDFs, and this is a so-called electron-ion collider at Brookhaven, which was already presented at the previous talks. So we are quite actively involved in making various predictions for the electron-ion collider. Now, for example, So the electron ion collider is very useful for studying the PDFs in the large X limit. Essentially, it can supersede the fixed target DS data that covers roughly the same region of X and Q. But also, this electron ion collider is quite useful for comparing against predictions of lattice QCD. I mentioned that PDFs cannot be computed from first principles yet, but lattice QCD predictions are getting quite close in obtaining quite reliable results for Mellin moments of Parton distribution functions and so-called quasi-PDFs and pseudo-PDFs. So this field is very rapidly progressing. In the case of the unpolarized PDFs, I believe the lattice QCD will still be behind the phenomenological studies like the CT studies for at least next 5 to 10 years. However, the lattice QCD can be very useful for predicting the combinations of PDFs or the types of PDFs like polarized PDFs that are not easy to measure in the experiment. And so therefore, what I believe will happen is that the global QCD analysis of unpolarized PDFs will continue to play an important role, and they will provide important results or important benchmark predictions for testing the new lattice QCD measurements. And so the lattice QCD measurements or calculations will be then used to predict the combinations of PDFs that cannot be easily extracted from the phenomenological data. So basically, there will be some kind of closed loop where the global QCD analysis provides some useful benchmark information for lattice QCD, and in turn, lattice QCD will predict results that are not easily derived in the global QCD analysis. Now, for example, we expect that the electron ion collider will play a major role in testing predictions of lattice QCD. The lattice QCD has the most power at large X values, precisely in the region where the EIC will provide very precise measurements. And so what you see in this figure are the sensitivity predictions for the EIC for the so-called quasi-PDFs Q bar at X at the X values that are shown on the horizontal axis, and this is for so-called iso vector U minus D combination at the factorization scale of 3 GeV. So what you see is that the EIC will be exceptionally powerful and sensitive to the to constraining the quasi-PDF, and this will provide the essential input for lattice QCD and deriving a better lattice QCD approaches. Okay, so I think this is all I wanted to tell you. So, and maybe I will finish by, just again to recapping that one part of my presentation focused on the CTEQ-TEA global QCD analysis. I encourage you to use these PDFs. We put a lot of effort into them, and it took us about 2 years to obtain reliable predictions. Now, basically, we see modest reduction in the PDF uncertainties on average, but there are some regions where you will see more prominent reduction of the PDF uncertainty. We found through this analysis that DES experiments dominate constraints on the PDFs and probably will continue to dominate them in the next 2 years. Now, the other point that I mentioned is that we do expect more data from the LHC to be included in the PDF feeds, but really for them to make a big impact, these measurements need to be brought into mutual agreement. So there must be some work happening at the level of the experiment to to better understand, for example, systematic effects in these measurements. So we have a number of PDF sets. So for example, if you really wish to probe the full range of the PDF uncertainty, you will use CT18 and CT18Z PDF sets. Now the CT18X and CT18Z include so-called saturation effect, or the approximation for the small X resummation. So therefore you can, for example, study how much the prediction for the gluon in the Higgs production region changes depending on our assumption about theory inherent deep inelastic scattering. And then I mentioned other new developments like the electron ion collider and the lattice QCD. Well, clearly there is a lot of future for this area, for this direction, the analysis of PDFs. And so therefore encourage you to collaborate with our group. And if you would like to join us, please let us know. Thank you so much.
Okay, yeah, no, thank you very much, Pavel. Let's give you a little applause here. All right, so questions. Go ahead and type speak in the chat window if you want to speak. Lucas, you had a question. Let's get you unmuted. Go for it, Lucas.
Hi. Yeah, thank you for the talk, Pavel. That was really interesting. For the sensitivity on the slide before, I think, for the EIC,
Just a sec.
I was just wondering for the negative X values, yeah, this one. For the negative X values, how come they're not
Yeah, so
the same as the
it's just a format for the presentation. So the way these quasi PDFs are presented, so the positive X corresponds to U minus D, but the negative X corresponds to D bar minus U bar. And that's because of the particular operator matrix elements that are computed in the case of the lattice QCD. But essentially the negative X in this case correspond to the D bar minus U bar combination.
Okay. So I guess naively, I would think that the negative would be the same as the positive X, but it doesn't look like it.
Yeah, because again, so on the right-hand side, you see the sensitivity essentially to D over D minus U.
Right.
On the right-hand side, you see U bar minus D bar. On the left-hand side, you see U bar minus, I think, let's see, no, I'm sorry. On the left-hand side, you see U bar minus D bar. On the right-hand side, you see U minus D. Yeah.
Okay, thank you.
Mm-hmm. Yeah.
So is then on the right-hand side, are you simply dominated by the fact that U and D are valence quarks in here so that they have a more prominent role of all the quarks?
Exactly, yeah.
Whereas on the left, you're probing exclusively the C, essentially then.
Right.
Okay. All right, yeah, we have a question from Bob. Okay, Bob, you should be good to unmute.
Okay, so yeah, Pavel, could you go to your last slide?
Which one?
It was the key points slide.
Yeah.
Yeah, so you indicated that the difference between CT18X and Z was this accounting for resummation.
Mm-hmm.
Can you, and I apologize if you described this before, I may have missed it, but how does that impact the PDFs? Like, where does that show up?
Yeah, so it shows up mostly in deep inelastic scattering at here at small x, and this region of DAS mostly probes the gluon at small x. So therefore, if you include the small x resummation effect, you basically account for the large logs of 1 minus x that appear in the hard cross section, and so you get I think a somewhat softer gluon at very small x. But then, because of the momentum sum rule that tells us that all the momentum fractions of all partons must add up to 1. So this constraint on the gluon at small x affects the gluon at large x. So through this compensating channel.
Mm-hmm. I see.
Mm-hmm.
Yeah. Okay.
Did you want to follow up, Bob, or are you?
I don't have a specific question, so no. I have an ambient question about where at the LHC this would have the biggest impact. Obviously, from what you just said, it would be areas where people are looking at things that have a lot of low PT gluon.
Yeah. Well, here is for example. Yeah.
Yeah. Go ahead. Yeah, I thought you probably did it, and it just, I think I probably didn't quite grok this slide. Yeah.
Yeah, but for example, if you look at the Parton luminosities, right? So you see the difference between the red band without the small x resummation and the green band, which also includes the small x resummation. And that shows how basically these differences are distributed.
Yeah, I see. Okay, thank you.
Mm-hmm.
Okay, and next up, Tim. You should be able to unmute, Tim.
Yeah, thanks, Steve. Thanks, Pavel. It was a really cool talk. So first of all, I just thought I'd say, I mean, in response to Lucas's question, I mean, the physical interpretation, what Pavel was showing was relevant for the lattice QCD calculations. I mean, so negative X has an interpretation when you do a lattice calculation, you're really measuring matrix elements of field operators, and positive, X has an interpretation of sort of a Parton momentum relative to a forward propagating nucleon. And so negative X is a backward propagating quark. So if you arbitrarily define the forward propagating direction to be for quarks, then negative X just by extension is anti-quark. So if you look at matrix elements as a function of positive x, you're probing correlation functions of quarks, and then by construction, then the negative x direction corresponds to the anti-quark distributions. So, and those are just totally different. That's why they're different in what Pavel was showing. But yeah, Pavel, I had a question. I was wondering if you had an opinion, just while you were talking, it occurred to me, do you have any either skepticism or hope or any feeling at all for how maybe the lattice in a few years might help with this cursive dimensionality? I mean, our perspective is in general, let's have some data and let the data sort of teach us how to parameterize things. But could you imagine maybe with more sophisticated lattice calculations having already a ballpark idea of how big the fits should be in terms of their parameterization size or the number of parameters or dimensions?
That's a good question, and so I don't know, and I think again, so what happens is that this curse of dimensionality is not an issue with a particular parameterization. I believe it's probably an issue with this overall approach. So we have, no matter what we do, whether lattice QCD or the phenomenological fits, we need to decide how many parameters to include in the PDF parameterization forms. And we believe that there should be at least 4 or 5 dynamic parameters per PDF flavor. So which means that if we target for a high precision, we should work at least with about 25, 30 parameters, no less than that. Right, and so then in the statistical analysis, this course of dimensionality will happen simply because we have this multi-dimensional probability distribution. And again, so we sort of know how to deal with it, and that's why we have these 2 complementary methods: the Hessian PDFs versus the NNPDF approach. They sort of address various issues that they can help us to more effectively to understand this multi-dimensional distribution and kind of avoid common pitfalls in studying.
Right. Yeah, because just, I mean, it might be naive, but what I could almost imagine is, say years down the road, on the basis of some sort of ab initio type QCD calculation, we could say, look, a certain number of PDF parameters is at least a minimum, and we could have more confidence in saying, all right, you're certainly overfitting. Just on formal grounds, we know that sort of the degrees of freedom that exist in the PDFs can't be so many, but I don't know, it's a sort of loosely formed thought, but I just thought I'd pick your brain.
It's a good possibility, right? So again, we do need additional inputs from the theory to help us constrain the let's say ambiguity in this Parton distribution function. In fact, well, the other difference between CT and NNPDF is that when we construct these parameterizations, we implement some additional theory considerations to prevent clearly unphysical combinations of the PDFs. For example, the combination where you will have more strange quarks than U-bar or D-bar quarks at very large x values, or very small x values.
Right.
And and then this additional theoretical prior is very helpful in constraining the PDF parametric forms.
Right. Yeah. Cool. Yeah. Thanks, Pavel.
And I don't see any other questions, Pavel, so I'm going to take a moment and ask one that's been bugging me, if that's okay with you.
Absolutely.
I want to dive into this issue about the tension between the LHC measurements a little bit, because I think it's very helpful to get your perspective on the following question. And pick an example if this is helpful for you. So pick a couple of measurements of 2 or 3 where there's tension and disagreement. And then I would be very curious to know, what is your reaction to that tension? I mean, for instance, what questions do you want the collaborations to answer based on this tension?
Well, I think the most prominent example is Atlas 7 TV Z and W production cross sections. And in fact, well, the other thing that I didn't mention is that, well, the CT18Z set, well, the other reason it is different is because it's the set that includes the special data. But the CT18 does not include it. And so now I don't know if I included this slide because I focused more on the gluon, but this Atlas 7 TV Z and W production prefers a very different strangeness PDF compared to, let's say, deep inelastic scattering. So then now, well, the issue is kind of like with the same issue like with the US presidential election. So if you have two different groups of data that prefer very different behavior of the PDFs, so if you can combine these 2 groups of data, you get let's see, a compromise between these data sets, but it is kind of an unstable compromise. You can even get a very small uncertainty bands if you, according to certain prescription for the uncertainty calculation. But it cannot be fully trusted because it is basically it's a field that has a significant tension between the experiments. Now, then how do we work around it? So I believe one thing is that, well, again, so there can be various ideas, but so far the collaborations were trying to produce new results as quickly as possible. And maybe what we should do is that we should also encourage people to work on this kind of going back and cross-checking the results or debugging the results, and implement sort of the standards for, let's say, accuracy or for benchmarking of the predictions that will kind of uniformly apply to all analysis. And hopefully through this, we may be able to, well, essentially resolve some of these tensions. Now, clearly, this is a major project, and there are many sources of systematic effects that happen in these measurements. But so I don't know how it will work out, but obviously some of these results need to be remeasured or repeated, and so again, so see if we can get a better insight into this. Now, a similar effort was done at Hera. So there were disagreeing measurements between H1 and Zeus, and they came up with so-called combined Hera data sets where they tried to cross-calibrate some of these measurements. Now, this is a major effort, and so therefore I don't expect it to happen right away. But I believe we will need this effort to really get the maximum out of these multiple measurements that currently can constrain the PDFs.
Okay. All right, and we'll take our last question or comment from Richard. Richard, you should be able to unmute.
It's a strange question. I have, maybe I'm wrong, but I have an impression that let's say the same flavor quarks are treated equally inside the analysis that leads to PDFs. Is there any effect possible if there are internal differences, like let's say 2 up and 1 down quark, and when the pair provides a doublet and the third one is just swirling around it? Is there any effect that you expect in the PDFs?
So no, Richard, but let me try to understand. So this is an effect coming from the
internal
dynamics.
The difference in internal interactions between quarks, which you assume have essentially complete asymptotic freedom, but they not necessarily do have it all the time, right?
Yeah. So the formalism should account for it, and so well, of course, the difference between, let's say, D quark and U quark PDFs somehow already accounts for this. Then there are the so-called high twist corrections that may contribute, and again, you have to remember that these formulas for the factorized cross sections that I was showing, they are valid up to some corrections, right? And so then the effects that you may discuss, like, well, I don't know if it's like, for example, non-universal effects, maybe not exactly what you mean, but they in principle they are there, but we expect that them to be very small, especially at the LHC. Right, but it is important to think about these issues. I agree with you that right now we don't have a clear evidence that it happens, but every time we see some, let's say, the tensions or some minor disagreements between experiments, we have to ask where the tension comes from. And one possibility, in some cases, may be this kind of effects, especially in the low energy data.
Thank you.
Okay, well, Tim, is it really urgent? Do you really need to speak? Let's get Tim unmuted here. Go for it, Tim.
Yeah, okay, thank you. I mean, just to really quickly comment on this, I can't resist saying, just because, Richard, you ask a very fundamental question. In some sense, if I understand your question correctly, that's sort of the point of all of this activity. I mean, one can formulate very specific models, for instance, that might be inspired by QCD that involve exactly the kinds of interactions that you just described that would leave very definite signatures in the PDFs. For instance, what's the behavior of the D quark versus the U quark at high X, for example, that what you would get would actually depend on exactly what you're just discussing. So that's one source of interest in this field in the first place. So I can't resist just making that little comment. Risk of drawing it out for just another.
Oh no, that's okay. I was just kidding. Richard, did you want to chat about that with Tim real fast? Or are you good?
We'll never finish because
but let me comment. So Jing, Tim, Alberto Accardi, and myself just wrote a paper where we look precisely for this kind of effects on D over U coming from using the deuteron data in the global analysis. And what we find, even though the deuteron data, if you look at this figure, so it sits in the large X and small q region, so it's somewhere here. But in fact, it does affect the predictions for D over U in the measurements of, let's say, the weak mixing angle in WZ production. And so then a very interesting question is what happens with this deuteron data? Do we include properly the nuclear corrections? So that's another major question that we'll have to address a few years from now. So you can see the paper on archive a few weeks ago.
Okay, excellent. Well, that's a perfect note to end on here. So Pavel, thank you very much. This was a really excellent talk. And if anyone in the audience is, curiosity is piqued about like how they can get involved in this work, Pavel, I'm assuming you just want them to reach out to you directly, right?
Absolutely. And please come to talk to me. Or on Wednesday, we can have our virtual lunches. And so we can discuss all of these issues in more detail.
Okay.
And thank you very much for your attention.
Oh, no, this was great. So thanks, everybody. And on that note, we'll go ahead and close out the event. Bye.
Bye-bye.